Hi, greetings from the mountain path. This is Ravichandran. Welcome back. This is the fifth session series on time series analysis and forecasting. Today we'll discuss introduction to ARIMA models, basics. Okay. So the session outline is ARIMA modeling, basic introduction. What is ARIMA? What is the expansion of ARIMA? What is AR, the auto-regressive component? What is the integrated component? And what is the moving average component? And putting together what is ARIMA PDQ model? And what are the steps to build up the model? So just a basic introduction to ARIMA model that we'll discuss today. So ARIMA stands for Autoregressive Integrated Moving Average. Is a technique for time series analysis and forecasting possible future values of time series. So ARIMA, Autoregressive Modeling and Moving Average, are two different approaches to forecasting time series data. So ARIMA integrates these two approaches, hence the name ARIMA. The forecasting is a branch of machine learning using the past behavior of time series to predict one or more future values of the time series. So what is an ARIMA model? Basically, it's a statistical model that forecasts time series using those past values and past forecasted errors. So basically, it's a univariate. It learns from its own variable own history from the past. It captures both the trend and the short-term momentum, but not the. So as you know, we're going to see that ARIMA model has got its own limitation. So one of the most widely used classical forecasting model is written as ARIMA PDQ. So ARIMA captures the trend, but it does not. Seasonality is not. So we use a different model as we discuss in due sessions. So what all the each letter in ARIMA model means? The AR means autoregressive. Autoregressive means uses the past values of the time series data. Integrated means it integrates both the AR and the MEA, but basically integrated means we are differencing the series to make the series stationary. Again, we'll discuss more on stationarity in the coming session. Moving average means and it uses the forecasted errors, the past errors. So we'll combine all the three, ARIMA, PDQ. So AR stands for autoregressive past values. I stands for differencing for non-stationary series into stationary. And MA is a moving average, we call it the past errors. So it is an autoregressive. So the current value depends upon is past values or past lags. Integrated means the data are differentiated to make the series stationary. Moving average, the current value is influenced by the past error terms or shocks. Now, so basically ARIMA model forecasting equation for a stationary time series is a linear regression type equation in which the predictors consisting of lags of independent variable and lags of forecasted errors. So basically predicted value of y is equal to a constant plus a weighted sum of the most recent values of y and a weighted sum of one or more recent values of errors. So that means ARIMA consisting of two parts. One is a constant plus the weighted sum of the recent past and the weighted sum of the and one of the recent values, the errors. So autoregressive component. Let's discuss what is autoregressive component. So autoregressive means predicts the value is a weighted sum of its own past value. So that means y hat is equal to constant plus and some coefficient into yt minus 1. So some quotient into yt minus 2, etc. So what is P? P, how many past time steps were used? Are we going to use 1 month back, 2 months back, or 1 day back, or 2 days back? So AR2 uses the two latest values, yt minus 1, yt minus 2. the recent observation carries the most weight. So today's value and tends to resemble yesterday. So what is the percentage of dependency on yesterday or 2 days back? That's what we are going to discuss. So AR equation, the auto-regressive component equation, is the predicted value, the value of the series time today is equal to yt is equal to a constant, we call it as an intercept, plus phi 1 into yt minus 1, phi 2 into yt minus 2, and so on. So how many lags we are going to take? How many p? P is the number of lags, the AR order. And then we discuss the last one, the epsilon is the white noise error term. So basically the AR equation consisting of a constant plus a phi 1 into yt minus 1, phi t into. So how many lags, that we will discuss as we proceed. The second part is integrated component. So generally whenever we see a time series which is non-stationary, how do you make the stationary series stationary? So that means a stationary series means a stable mean and a variance, absolutely no trend. So how do you make this? That means we use a concept called differencing. That means subtract the previous values, that is yt minus yt minus 1. So we'll again discuss how we are going to do stationary testing and how you are going to make the data a non-stationary to stationary in the next session. So order D means how many times we do the differencing. So D, mostly it won't be more than 2. Most of the times as soon as we do differencing once, the series will see that this becomes stationary. So stationary series is required before modeling. So it's a requirement for a basic ARIMA model. So now look at this diagram here. As soon as you see the series, you can see that it shows a very clear upward trend. That means it's a non-stationary series. So when we do the differencing, we can see this, the same series becomes stationary with more or less a constant mean and the trend reversal. So that is a very important aspect of a ARIMA model, to convert a non-stationary into stationary by differencing. The third important area is a component is a moving average component. So we are using the past forecasted errors, not the past values. So that means each error, that is a current error, epsilon t is equal to actual minus the predicted. What is an error? It is always actual minus the predicted. That is nothing but the difference. So order Q depends upon how many past errors we are going to use. So when you say MA1, that means we are going to use the recent epsilon t minus 1. Let the model react to these. So the basic ARIMA model is consisting of AR, PDQ. So if you put the MA equation alone, a constant term, an error shock, ET today, plus theta into, we call it as theta into epsilon t minus 1, theta into epsilon t1, go on. So basically, the ARIMA model is consisting of AR and the MA component, and the D is nothing but how many times we use the differencing. Now, putting all together, an ARIMA model, PDQ, P, the AR order, how many past values? It can be AR1, AR2 like that. D, differencing. So differencing can be D1 or D2. MA order. So MA1, MA2 like that. But there's no requirement that all the ARIMA models should have a PDQ. So you may have AR100 model. There's no differencing, there's no MA. You may have AR011. That means you have no AR order. You have only one differencing. Then you have what is called one moving error. So you can have a different combinations of a ARPD. So how you determine the PDQ, that we will discuss as we proceed. So P is the number of autoregressive lag terms. D is the number of differencing. How many times your data is differenced to make it stationary. Q is the number of moving average error terms. When you say AR111, that means AR1 term, first differencing and MA1 term. Now, so the P denotes the number of autoaggressive terms, D denotes the number of differencing terms, Q denotes the number of and times it is a moving average. There is nothing but how many times the errors, past errors we discuss. That's the main. So let's discuss a different combination. Case 1. Let's look at the ARP00 model. And you can have AR100 or you can have AR200 or ARP0 general model. That means constant plus and you can see that you can always say and phi into xt minus 1 or yt minus 1. So for a AR2 model, constant plus and phi 1 into xt minus 1, phi 2 into xt minus 2, like that. So this is a case 1 simple model. Case 2, you have a 00Q model. That means it's a pure moving average model. So that means there is no differencing, there is no AR model. You can say that the xt is equal to, and there's nothing but the epsilon t, the current error, plus of phi and theta into epsilon t minus 1, like that. So you can, it's a pure moving average model. Third one is we don't have AR component, so we don't have a MA component, so we can call it as a pure random walk model. So that means there's no, the series is non-stationary. The simplest model we can see is a random model. That means there is a constant plus xt minus 1. That means today's price or today's value depends upon a mu, a constant, plus the previous value. That's all. So that means it is a pure random model. Case 4, we can have a PDQ model. That means we can have combinations of AR1, AR, that is PDQ. That means we can have 1D0 or you can have 2D0 or you can have PD. That means a full ARQ. So we can have a combinations of PDQ. So this is if the series is stationary, that means it is autocorrelated. Perhaps we can predict at a multiple of its own previous value plus a constant and plus the previous errors. So ARIMA model, and though it a very basic model, is simple, but again the challenge comes. And first step, so what are the steps? So we are going to what are the steps to actually build a basic ARIMA model. A basic ARIMA model, first visualize for stationarity, whether the series has a trend. So then you test it. In Excel we can simply test, simple test, or you can use a ADF test to whether the series is stationary. Then you can, after differencing, then once you decide the series is non-stationary, then you make it stationary by differencing it. So apply the difference, remove the trend. So we are only able to remove the trend and choose a D. Then the third important step is a very big step. How to identify the P and Q? So that means how many lags. So we have to calculate what is called autocorrelation and partial autocorrelation plots. So we are going to discuss in the next session. Then fit the model, estimate the PDQ, and then validate and forecast. See, these are all the basic steps of a ARIMA model. Now, so what is called the Box-Jenkins method. In 1970, the statistician George Box and Gwilym Jenkins proposed what has become known as the Box-Jenkins method to fit any kind of time series model. So this approach starts with the assumption that the process generated the time series can be approximated and using a model only if it is stationary. So stationary is a requirement. So it consisting of 4 steps. So Box-Jenkins method is the first model identification. So how do you model that in PDQ in ARIMA model? So what is the P order and the AR model and the MA order and the D differencing. Then we have to estimate the parameters. So parameters and that is a coefficient. So we have to estimate phi and what is called the theta. We have to estimate the very important. Then in Excel also we can do it. So in ARIMA model, in simple spreadsheet, as we proceed, we will going to discuss the model diagnostic, whether the model and the chosen model it is perfect. Then we can do the forecasting. So we will do a lot of steps. So key takeaway from this discussion. So we have discussed what is an ARIMA model, auto-regressive and integrated moving average model. Then what are the PDQ? What does it represent? So AR uses the past values, MA uses the past errors, I is used to make the non-stationary data stationary by using differencing. Then what is called the Box-Jenkins flow. Test, difference, fit and forecast. So ARIMA model combines simplicity, power for effective time series forecasting. So thanks for watching. In the next series, we will go through Excel. What is that? We'll do some illustration on what is time series, what is stationary. So how do you test for stationarity? What are the simple methods in Excel apart from visualization? And then how do you make this non-stationary data stationary by using differencing? So thank you for watching. Thank you.